in level 100 first semester, we were introduced to Introduction to Statistics and Probability. We were taken through the concept of statistics, sample data collection processes and stuff, different types of statistics, and different areas of study. Then we were also introduced to basic probability and some definitions. So I have to admit these people before we proceed. Thank you for understanding. So what we'll be doing this semester, we'll look at brief recap of what we did in the latter part of first semester, Stat 111, which will look at introduction to probability. That's a basic concept in probability. We'll look at a random experiment, look at definition of probability, we'll look at axioms and laws of probability. We'll go and look at the expectation of random variable. Then look at conditional probability and Bayes rule. Ideally, we're supposed to do this in the first semester, but because of how rushed the course was and how heavy it was, all was not covered, and we're not even examining on this latter part. So what we'll be doing this semester, we'll recap this and proceed to look at probability and 8 other known distributions. So we'll be looking at distributions of continuous and discrete random variables. Then we'll also continue to look at familiar. We'll look at familiar distributions, both of discrete and continuous. We'll only be introduced to that and know how to apply them to solve problems. Ideally, we will not be going much details into that. So kindly bear with us. Please let me admit these students who have just joined, who are in the waiting room. So maybe when we start with the Zoom, there will be no need of switching out because the person can able to enter when you are late. Enter right away, starting from next week.
Have a nice day.
Good. Okay. Please. So, for that, and that will be part of our assessment. We will also have one interview assessment, which will be online. That one will be specified. If it is 1 hour, we will specify 1 hour time, which will be the same real time scenario, which all of us will do that time. Then when it's done, that is all. So if we have to do an IE or interim assessment or mid-semester exam, if it is on Saturday, that we'll do that. It can be maybe from 5:30 to 7:30, then we are done. There'll be nothing like considering late or anything of that sort. So let us take note, and if that, we will discuss that before that will be done. And exercises will be given so that during the midweek, we can able to do that and upgrade and be with time as we proceed. Okay. So for the first lecture, we'll be looking at a recap of all of this. And this is what is the main purpose of the lecture 1. The purpose of this session is to equip students with basic knowledge and skills in probability. And this session, students will be introduced to basic concepts in probability, such as random events, random variables, expectation of random variables, and conditional events and probabilities, which will also include independent events and probability, total probability rule, and Bayes theorem. Please, based on the course, if you have any question, kindly let me know before we begin. So these are the key outcomes that we expected of us at the end of the lecture. Define and distinguish between random events and random variables. State examples of random events and random variables, define the expectation of a random variable, calculate an expectation of a given probability function, understand dependent and independent events, calculate the conditional probabilities of random events, then apply the total probability rule and Bayes theorem to solve real-life problems. Any question? Are we okay with the learning outcome for this lecture? If I'm running too fast, can you let me know? You can use the chat session or the reactions there to alert me if you have a question or I'm running too fast. Okay, so we'll begin with random experiments. It's my hope that we were able to learn that in the last semester. An experiment is a process of observations. So we defined experiment is a process of observation. It can be just standing at a junction looking at the number of cars that pass. So you may be interested in a particular car and look at how many times that particular brand or model or type of model the car passes in that junction. It's an experiment that you are observing. So when we talk about random experiment, it's any process of observations or activity in which the results cannot be predicted with certainty. It's a certainty with a sure event. We cannot predict it with 100% surety. If such a process of observation or activity is performed and we cannot predict the outcome with 100% certainty or surety, then we say that it is a random experiment. So an example is throwing a Ludo die, which has 6 surfaces numbered 1, 2, 3, 4, 5, up to 6. So in that case, we cannot predict with certainty or with 100% sure that when you draw a die, 1 will occur or 2 will occur. So that means that throwing a die or flipping a coin is a random experiment. Alternatively, an experiment or random experiment is any specified set of actions where the results cannot be predicted with certainty. So in statistics, when we perform an experiment where the result cannot be specified or predicted with certainty, then we say that we are performing a random experiment, which will lead us to a sample space. Okay. So we have some examples here. Experiment repetition of an experiment is called a trial. Typical examples of random experiments are the roll of a die, the toss of a coin, and selecting a ball at random from a box containing 3 balls marked A, B, and C. So these are some examples of random experiments that we normally consider. We can also look at a situation where we have playing cards where we shuffle them and we pick one at random. Let me admit these students so that we proceed. Okay. Any question with this before we proceed to the next one? Are we okay with the definition of a random experiment? So let's continue with some terminologies that we'll be needing in this process. We'll be looking at outcomes, events, and sample space. Get results. Results can be grouped as outcomes, events. So one side denoted as the tail and the other side denoted as the head. Flip it, that becomes an outcome. So any outcome or any result that we collect from performing an experiment or a random experiment is referred to as outcomes. Then events are a collection or a set of what? Of outcome that denoted the interest of the experiment. So any collection of outcomes of a random experiment becomes what? Your event. So if I flip a Ludo die, and if what I'm interested is 1 and 2, then my event is what? 1 and 2. So 3, 4, 5, 6 are not what I'm interested. So the collection of what? These two outcomes becomes my what? Event. Then when you talk about a sample space, it's also what? It's also a set which is what? Denoted as a collection of all possible outcomes. So in an example of what? Flipping a Ludo die, the collection of 1, 2, 3, 4, 5, 6 together. And with this, there's no other outcome that can come in performing throwing a Ludo die. Then we refer to this set as your sample space, which in other sense can be referred to as your universal set when you come to the set theory. So an outcome is a result of an experiment. What we perform as what you get is an outcome. So example is a fed coin is tossed once. The result is either a head or a tail. So which are known as outcomes. So a head is an outcome, a tail is also an outcome. When we come to an event is any collection of outcomes. And a simple event is an event with only one possible outcome. So any collection of outcomes of a random experiment is referred to as an event. So it can be 1, it can be 2 outcomes, it can be 3, it can even be a total outcome. So that is becomes our event. So if it is only 1 outcome in that set, then we call it as a simple event. If it is more than 1, then we call it as a composite or complex event. So in tossing a fair die once, the possible outcomes are 1, 2, 3, 4, 5, 6. So the collection of 1 or more of these possible outcomes is an event. So you can have example 1, 2, 3, or 4. All these are what? Outcome of events, which is the collection of what? Outcome. Then the third terminology is a sample space, normally referred to as a universal set under all elements under consideration. So the sample space S, normally we denote it by S or omega, which is the Greek letter of a given experiment, is the set that contains all possible outcomes of the experiment. So the set that collects all possible outcomes of the experiment is your sample space. So in an example of a Ludo die, the set that contains all the possible outcomes of a Ludo die is your sample space. So the possible outcomes are 1, 2, 3, 4, 5, and 6. When we come to a tail, so head and a tail, collection of that as a set becomes of your sample space. Let me outcome. One or more is your event. And the result that we get are outcomes. Note that a set with one simple point is often referred to as an elementary event. A set with only one sample point is an elementary event. And a set A is called a subset of B, denoted by A. Subset of B is also an element of B. Any subset of the sample space is called an event. So if you take any subset of the sample space, so we know from our set theory that A is a subset of B. And A is also a subset of the sample space, capital X. So your sample space S is the subset of itself. That can be written as what we have here, because it contains all the elements. So we say that equal subset of improper subset of S. Since S is the set of all possible outcomes of the experiment, it is often referred to as certain event, meaning a sure event. So that event is certain. That no matter whatever you want to perform, each and any of the elements in that set will occur. So we call it a certain event or a sure event. Any question? Let me admit the new students who have joined, who are in the waiting room, please. Okay. So let's move on to another example. Find the sample space of an experiment of tossing a coin repeatedly and counting the number of tosses required until the first head appeared. So the sample space, it means that we're tossing the coin repeatedly. What happens that we can toss the first one and that first one can give us the head, or we can toss the first one, it will not give us a head. We have to continue and toss the second one will give us the head. Or we can toss it 3 times and the third one will be the head, or we can do it infinite time. So your sample space will be what? 1, 2, 3, 4, 5, up to infinity. That's the number of repetitions that we perform. So sometimes we can have a sample space which is countably what? Infinite, or finite, countably finite, or within an interval, a range of interval which takes decimal values. Let's look at a second example. Consider an experiment of drawing 2 cards at random from a bag containing 4 cards marked with the integers 1, 2, 3, 4. So find the sample space S1 of the experiment if the first card drawn is not replaced. Let the first number indicate the number of the first card drawn. So we are coming to draw the card. When we pick the first one, we will not replace. So we can have now, when we have to draw it 2 times. So you pick the first one, you don't replace, and you pick the second one. You get it? So the first one can be 1, the second one can be 2, or the first one can be 2, the second one can be 1, in that order. So we have to get the sample space. And the second scenario is that find the sample space S2 of the experiment if the first card drawn is replaced before the second one is drawn. So this will be our sample space. So the sample space X1, which is what contains 12 ordered pairs, Ij, where I is not equal to j. I mean, if I pick one, I will not replace before I pick the second one. So one will not appear twice. You can't pick one 2 times. So your sample space can be 1, 2, or 1, 3, 1, 4, 2, 1, or 2, 3, or 2, 4, or 3, 1, 3, 2, 3, 4, or 4, 1, 4, 2, or 4, 3. In a second scenario, you pick, you replace before you pick again. In that order, you can have the first one 1 and the second one also be 1. You can have the first one and the second one can be 2. Second scenario, we will have 1, 1, 2, 2, 3, 3, and 4, 4, which make the ordered pairs 16 sample points.
To generate the answers you just showed us, so you have to use your own discretion to generate something like this.
Okay. Then there's also another hand. That's all. Yes. So, with for example, the first one, see that with their pairs, you are drawing the first one and pick the second one. The formula is that what your I and the card you pick ranging between 1 and 4, and it's either what I running from 1 to 4, J running from 1 to also 4. However, you will not have what I equals to J. You will not have a situation where 1 will be equals to what? The I will be equals to J. So it means that picking without replacement, you cannot pick one card in the word drawing twice, one or twice. So you can't pick a card number 1 2 times. You can only pick it once, because when you pick it, you cannot replace before you pick the second one. So in that scenario, if I pick the first one is 1, I will not draw it and before picking the second one. So the second one will not be contained in that bag again. I will only be left with 2, 3, 4. So it means that the second one will either be 2 or 3 or 4. So that is the formula we put here. Your I and J are the numbers written enable your cards from 1 to 4 for the first draw and the second one. In the second scenario, in this case, when I pick, there are 4 cards in the box, labelable 1, 2, 3, 4. When I pick the first one, I'll put it back before I pick the second one. So in that case, there's a possibility that I can pick that one card 2 times, or I can pick the first one separate and the second one will be a different card. So in that case, having 1, 1 is what? Different. That means that the first one was the same card. And when I put it and I pick again, it was still the same card. In the second scenario, I picked the first one was 1, but when I drop it and I pick again, it wasn't 1, it was 2. Meaning here we replace it. So if you do that, you can have what? Any card can be picked twice. So that is why we have 1, 1, we have 2, 2, we have 3, 3, we have 4, 4. So each card was picked twice in that scenario. That is the possibility. This is your question answered, the two of you.
Yes, sir. It's answered.
Thank you. Okay. So we can proceed. Let me admit these students who have just joined again. Okay, Victoria, you have your hand is up. And Vida, please, can you ask your questions?
Yes.
Victoria first.
Hello, sir. Please, with the formulas, you have to deduce it yourself, right?
The formula, ideally, you don't need to deduce it. You only have to look at how you pick your cards from the box. Just like you have mangoes numbered 4 mangoes numbered 1, 2, 3, 4, and you are in a box, and you have to pick 2. If you pick, there's a possibility that when you pick the first one, you put it back and you pick the second one. So you can pick that one mango, the same mango 2 times. Is that okay? Is that right?
Yeah.
It's also possible that you can pick the first one and you put it back and you pick the second one also be different. Is that okay?
Yes, please.
Okay, so that is how we came by this table here. That since they are numbered 1, 2, 3 up to 4, it is possible that the first one can be 1, and the second one that will pick, since I will replace it, it can also be 1. It's also possible that the first one can be 2, but since I'll put it back, the second one can be what? 1. Or the first one, when I pick it is 2. When I replace it and I pick again, it can be 2. So all these are some of the possibilities that can occur in drawing what? 2 cards simultaneously from the what? Box with replacement. In the first one, you pick it, you don't replace before you pick again. So there are 4. So if I pick 1 and I don't put it back, automatically they'll be left with 3. So there's no possible that I can able to pick a particular card twice. Is that okay? So based on this scenario, that is why we came out with these numbers where I is not equal to J, because we are not replacing. So if we are not replacing, I will not be equal to J. I mean, the first one will not be the same as the second time you pick again. You don't have a card being picked twice. You can only pick 1 card at the same time, at a time. In the second scenario, since we will replace it and pick again, it is possible that we can pick the first one, and if you put it back, and we can also pick 1 again. So that's why we didn't say that I is not equal to J, but we only say that the first picking, we can pick either 1, 2, 3, 4. And the second picking, we can also pick 1, 2, 3, 4. So that is what we display here as your sample point. Is it okay now?
Yes, sir.
Yes, sir. Thank you so much.
You are welcome. And thank you for asking these questions so that it can be more clearable, understandable. Okay. So let's look at another example 3. Find the sample space for the experiment of measuring in hours the lifetime of a transistor. So we learned that in start 111 that when we talk of a variable, when we are doing measurement, we will get a continuous random variable. Continuous, especially measuring times height or distance. We can get fraction, decimal fraction. So a sample space for a variable that we are experimenting, that we are doing measurement, we should be considering what? Decimals between 0 and infinity for measurement. So that is what will come to our mind. But when we are counting, then we should have a discrete observation. That's finite, countable. So clearly, all possible outcomes are all positive real numbers. That is, the lifetime can take all values on a positive number line. That's sample space S is given by X between 0 and infinity. Meaning that if it is 0, that means the samples, the experiment of measuring lifetime transistor was 0. There was no life. When you test it, there was no hour before it failed. It failed at the factory. But maybe if it is 1 hour, it means that after 1 hour, it will fail. That is what it means by that. So you can get your hours to be from 0 to infinity. So we have to note that it is useful to distinguish between two types of sample spaces, discrete and continuous. A sample space is discrete if it contains a finite or countable infinite set of possible outcomes. In this case, the element in the sample space can be listed or the list does not terminate, as in example 1. So we can have discrete and continue. In example 1, we have our list to infinity. That's 1, 2, 3. We can do it repeatedly to infinity. That's countably infinite. In example 2, we have this as what? This outcome, which is counting the number. This. In example 3, we have infinite. That's a continuous sample space, which range between 0 and infinity. That's all. Either finite in an interval or infinite. So we should be able to understand when we have a discrete sample space. It's a Sorry for that. Thank you very much. So I'm back. Let me admit these people again. Yeah. Okay, so we will now look at the random variable and its definition. Are we okay with our sample space event and type of sample space do we have?
Yes, sir.
Okay. So let's look at what a random variable is. By definition, a random variable, usually written as X in statistics, in IT or in computer science, is a placeholder of numbers. It used to hold a place for numbers or values or what have you. So when you look at the IT point of view, it's just a placeholder. When you talk about a placeholder or a random variable, it's just a place, something to assign values to numbers or item or measurement. So a random variable, usually written as X, is a variable whose possible values are numerical outcomes of a random phenomenon. So it can be discrete or it can be continuous. They are numerical values of this thing. So maybe you want to measure age. So you can put a placeholder for age in your IT, which will in your computer, which will collect your age of student. So that placeholder is just collecting the age of student, and then it becomes random because all the ages that you collect will not be the same. Are we okay? Will not be, it will not be 20 years or if it is 20 years or all the students are 20 years, that means it is no more a random but rather a constant. But some may be 20 years, some may be 10 years, some may be 15, some may be 16, some may be 17, some may be 18. Is that okay? So we define that as a random variable. It can be also a placeholder by denoting the sex of a respondent. It can be either male or female, or it can be your place of residence. Where do you stay? Whether in the Tamale or Kumasi or Cape Coast or what have you. These are all definition of random variable. So it's just a measurement or a count of a distance. So in alternatively, we can also define a random variable is a variable whose value is unknown or a function that assigns values to each of an experiment's outcomes. In this case, experiment outcome, if you go and take a questionnaire and interview people, you're asking them for their age, because you are not certain. You are performing an experiment. If I get to town and ask and take 20 people, ask of their ages, I don't know their age, so I'm not certain. So as you ask them, the outcome you get you assign them to what? As age, then that becomes a random variable. Sometimes you can get to people, ask them of their gender. I want to interview 20 people. You are the first one, maybe it's a male, the second one is a female, in that order. It's also what known as a random variable. So it's an experiment that you are performing. So the outcome of a experiment being assigned value to becomes your random variable. So random variables are often designated by letters X, Y, Z in statistics and can be classified as discrete, which are variables that have specific values, that's integers, or continuous, which are variables that can have any value within a continuous range. Maybe you can have a variable which is between 0 and 2. It can be 0.1, 0.001, or it can be 0.5, it can be 1.2 or 1 or this thing. When you have a variable which contains both decimal values, that means it's a continuous random variable. But if it's only contained in, then say that it's a discrete random variable. Okay. I have two persons here also to admit. So, Lord willing, next week, because of this, next we will be using Zoom, so that I'll send the link to your course rep to share with you, as we all agreed. So we have examples of random variables. A typical example of a random variable is the outcome of a coin toss. When you toss a coin, the random variable y is the number of heads we obtain from tossing 2 coins. Then y could be 0, 1, 2. If I toss 2 coins, I'll either get 2 heads or only 1 head or 0 head at all. 0 head means that all the 2 coins give me tail. If I get 1 head, it means that the first one was a head, the second one was tail, or the first one was a tail, the second one was a head. If I have 2 heads, it means the 2 coins gave me what? Or the 2 tosses gave me heads at what they say at the first or the second time. Then your 0, 1, 2 becomes what? The values of your random variable. So here we have assigned what? Function to our experiment outcome, and that gives us a random variable y, which is the number of heads in tossing 2 coins or tossing a coin 2 times. Example of a discrete random variable include the number of children. So when you go to a family, want to see the number of children, then we can able to maybe in the one family with 0, some can be 2, some can be 3, some can be 100 in that order. So that is also can be a random which we assign count by using the count function, the number of children in a family. Another one, a continuous example, is a random variable are usually measurement. So continuous random variable are usually what? Measurement. Examples include you take the height of people or patients or individual or weight. Especially when you go to the hospital, the people will be interested to measure your weight, your height, and is able to calculate whether you are obese or whether you are overweight or whether you are underweight or normal. So BMI. So they will calculate, you take your height and measure your weight. And with that, they will be able to use to calculate your BMI. You also may want to find out what is your weight, like so that they can able to prescribe some this thing for you. When all these measurements, since it's a continuous variable, you have the decimals, we call them as well continuous variable because they are measurement that we do. Some can look at the weight of sugar. We can also look at the weight of orange or time required to run a mile. That will all give you continuous random variable. Any question? Are we okay? So if we are okay with that, we can go on to look at definition of probability. Chance and the assessment of risk play a part in everyone's life. Most often we define probability as the chances that we take or the risk or assessment that we take in everyday life. So as individuals, we take risks at every point in time. We calculate our probability or chances of events occurring or how we take our move. Even if you want to do an investment, we consider by looking at what are the chances that I may make profit, what are the chances that I'll lose, or if you want to take a decision, you ask what are the chances, what is the percentage that I'm making a correct decision, that this decision that I'm taking will favor me, give me a brighter future, or what is the chances that this decision that I'm taking will give me will set me back or lead me to a misfortune and stuff. When we do all that, we are applying probability in our daily lives. So as a loan officer, you may want to evaluate the probability or the chances that a customer may default. So maybe you are in a company giving out loans. Maybe the whole year you give out loan to 100 people. Out of this 100, only 2 were not able to pay the loan. 98 were able to pay. So the chances that when the following year you are giving loan out that somebody will default or will not pay back, you look at maybe 2%, because out of the 100, 2 were not able to pay. So your idea will be 2%. So when you are giving out, you have to consider all that when you are increasing. So if you increase people to 300, what are the chances that they may not pay? So you expect that if it is 300, then you are expecting more than 2% will be like 6 people who will not be able to pay. So you factor all that in place, and that is what we are defining as probability. So probability has found a wide range of businesses applications, such as calculation of risk in the banking and insurance industries, quality control, and market research. Most events in life are unpredictable. That events in life are non-deterministic. You can't predict them with certainty because they are non-deterministic. That means they are random. Events in life are random. We sleep, we are not certain whether we are able to wake up. People sleep and they are not able to wake up the following day, they die. Some too, you go and work, you are not able, you fall sick and you find yourself in the hospital. So life is not constant, it's not constant, but rather we call it not deterministic, but rather random or stochastic. So that is why we cannot predict tomorrow with certainty. Is that okay? So these are the chances. Though we wake up every day, we sleep and wake up every day, but we are not certain that if I sleep today, tomorrow I'll wake up early or wake up. It's possible I may pass to the next life. So that is what we mean by our life is unpredictable. If the world is treated as stochastic, then we can measure the chances of any part in a given situation. Okay, are we with me? So if that, let's look at the definition. Probability is the measure of the likelihood of the occurrence of an event. The probability of an event can be thought of as the relative frequency of the event. The probability of an outcome can also be interpreted as a subjective probability or degree of belief that the outcome will occur. Then we also know that probabilities are value numbers between 0 and 1, which we look at that detail later. An event with probability 0 has no chance of occurring, and an event with probability 1 is certain to occur. Other definitions of probability are relative frequency and classical definitions of probability. So we can look at relative frequency, classical definition. We'll look at them one after the other. So the mathematical measure of the likelihood of an occurrence of an event is defined as so. About relative frequency or classical, we'll look at them when we refer to what subjective, classical, and what relative frequency. When we talk about relative frequency, let's look at so you have what you go to the field and collect data of 200 people. Out of these 200 people, 150 were males and 50 were female. So what are the chances that what when you go back to that population, you get what female? You when you select, you get a female, or when you select, you get what you interview someone based on the previous survey you have done. You know that out of 200 people that is sampled from the population, 150 were males and there were 50 were females. And the chances of interview somebody from the population to be a female will be what 50 over 200, and interview someone who will be 150 over 200. In that case, we refer to that as a relative frequency probability. And with relative frequency, it also tells you that when you increase your sample size, it becomes your probability of that event occurring the same as the probability of the total population of that particular event. So another example is that, for instance, I have a Ludo die or a coin. I know that the one side is tail and the other side is also a head. When you flip that, the chances that the probability that a head will occur is 0.5. The chances that a tail will also occur is 0.5. So that probability is referred to as a classical probability. But if you repeat this process for 100 times, what are the chances that you will get a head, and how many times will give you a tail? Do you get it? It can happen in the hand of 100 times that you flip a coin. 45 may be a head, and the remaining 55 may be a tail. That tells you that that is not equal to a classical probability, which is what 0.5, 0.5. But if you increase the number of repetition to say like 1,000, it's likely that the probability or the chances that a head will occur will be the same as a tail will occur, and that becomes your relative probability that we are talking about. So let's go ahead and define that. So the relative frequency definition that the probability of an outcome is interpreted as the limiting value of the proportion of times the outcome occurs in n repetitions of the random experiment as n increases beyond bound. So when you increase the number of repetitions beyond bound, meaning it approaches infinity, then what? The limit as n approaches infinity, the probability of that event occur over the total frequency will be equal to the classical probability. That is what we are referring to as relative frequency probability. Because it's talking about the number of times a particular number of event occur over the total number of repetitions that we perform in that experiment. So that is what, so for example, if we assign a probability of 0.4 to the outcome that there is a defective item in a production batch, we might interpret this assignment as implying that if we analyze many items in the production batch, probably 40% of the items will be defective. So means that if I take any 100 of them, 40% will be, or 40 of them will not be good. Only 60 will be good. That is what we refer to as classical probability assignment. But if you continue in that way, it becomes a frequency, probability, or interpretation. So what I explained as well, the probability of event A occurring. So N of A is the number of times event A occur over the total number of repetitions or number of times. So as N approaching infinity, this probability becomes the probability that of event in the total population. Means that if you consider the entire population of that community of that item being produced, the probability that that event will occur will be just as, or if you take a sample of that. So that's what we refer to as relative frequency probability. So the number of times that event occur over a total number of frequency. So as you increase your sample size, meaning you are approaching the total population. So it means that it becomes the population probability. Any question with this definition? I'm sorry for moving up and down. It's because I have to try to be admitting all these people as we proceed. So that's why. So we have an example here. The table below shows the frequency distribution of grades in statistics class. So we have system marks 75, 8, 78 up to 99. So how many people score system was 1, 75, 3, 78, 5, 4, 85 in that order. So now the relative probability, the relative frequency for mark 90 is computed as the number of people who had 90 mark over a total number of students that took the exam. And that will be 5 over 63. So 0.079 becomes the relative frequency of the 90 mark, which is referred to as the probability. We can also be asked why the relative frequency for obtaining a mark less than or equal to 83. So you add all the frequencies from 60 to 6 to 8. 1 plus 3 plus 4 plus 5 plus 7. That will give you 20 over 63. Okay, using the relative, we can therefore estimate the probabilities. That's the probability of obtaining a mark 90 and obtain a mark less than or equal to 83. So we learned in start 111 relative frequency is the same as the probability for that particular class or mark. So classical definition, which we refer to as an equally likely model. We know that when we flip a coin, it has two sides. So the probability that head will occur is the same as the probability that tail will occur. So they both have equal likelihood events, and that we call classical probability. But if you look also a Ludo die, when you throw a Ludo die, it has 6 sides. Each side has equal chances of occurring. 1, 2, 3. So the probability of 1 occurring is the same as the probability that 2 occur, same as 3, same as 4, same as 5. So it's 1 over 6, 1 over 6, 1 over 6. So refer to this as a classical definition of probability. Okay. So when you also consider, when we talk about individual sample, we also consider individual from the sample as equally likely event because we randomly select the people using either simple random sampling or stratified random sampling or cluster sampling or multi-stage sampling or what have you. So in that instant, or systematic sampling, in that each of them are equally likely events. So we refer to that as well. Equal classical probability, which we count the number of times that individual characteristics occur on the sample. So suppose there are 5 balls in a box, 3 balls are red and 2 are black. The box is shaken and the ball is selected without looking. What is the probability that this ball is red? So with the classical definition, each ball in the box has the same probability of occurring, the same chance of occurring. So there are 3 balls which are what? Red, and 2 balls which are, so each of them is one, each ball is 1/5, 1/5, 1/5. So since 3 are red, the probability red ball will occur will be 3 out of 5. And the chances that a black ball will occur will be 2/5. So these are what we refer to the classical example of probability. So we have another example with a sample data. In a group of 400 college students, there are 170 science majors and 230 non-science majors. Of these, science major 55 are women, and there are 120 women. And there are 120 women non-science major. One student is selected at random from the group. Find the probability that the selected student is A, science major, B, 2, a woman, and 3, neither a woman nor science major. So for science major, you look at how many of them are science major. These are science major. So you count 55 plus 115, that'll be 170. So 170 are science major. So 170 over the total number of students, that's what? 400. So the probability that someone is science major will be what? The number of students who are science major over the total number of students, that's 170 over 400. The second one, the probability that is a woman. So look at the total number of women. Come again.
Yeah, please take that part again.
Okay. Let me admit these students.
I can't see your screen.
I'm coming. I'm meeting some of the students who are in the waiting room. Can you see my screen now? Can we see my screen now?
Yes, sir.
Okay.
Yes, sir.
I'm saying that for those who are science majors, the first column is science major and second one is for non-science major. Is that okay? So if I to find the probability that a student is selected is a science major, any student, any of these 170 students can be the one selected. So since all of them are equal likely event, so for science major, it will be the total number of science majors over the total number of students in the survey. So it will be 170 over 400. So 170 is your event as science major, and your sample space is 400. So the probability that is a science major will be the number of events or number of people who are science major over the total number of people in the class. That will be 170 over 2 over 400. That will give us our probability. Then in the other one,
Okay.
we want women. Yes.
Sir, please, so the sample space, you come and okay, thank you.
Because it's a probability, you have to divide it by a sample space. So your probability between 0 and 1. So that's why we are dividing it by total or sample space.
Hello,
So
sir.
when we come, yes.
Sir, please, can you cancel out?
Yes. You can simplify it to the smallest fraction. It's allowed.
Okay.
You can even divide it and get your decimal to make sure that between 0 and 1. You shouldn't
Okay,
go
sir, thank you.
bigger than 1 or go less than 0.
Thank you, sir.
You are welcome. Secondly, we have to find out that the person selected is a woman. So if the person selected is a woman, you look for how many are women in the world, in the survey. And we realize that those who are science major are 55, those who are non-science major are 120. So you add the two, that will give you 175. So 170 were the total women. So the probability that a woman is selected will be equal to 1, the total number of women, over the total sample space. So that is why we have number of women were 175. So the probability a woman will be selected will be what? 175 over 400. This one too, you need to cancel it to the smaller. If you can cancel, if you want to live in the fraction, no problem. Then finally, we have to find neither a woman nor science major. It shouldn't be a woman. So you rule out the horizontal line here. And also no a science major. It shouldn't be a woman or a science major. So if it's not a woman, we cancel the first rule out. If it's not a science major, we cancel the first rule out. So what will be left is just 110. So men who were non-science students, that's the people they are looking for. So the probability is neither a woman nor a science major means only men who were non-science major, which is 110. So 110 over the total sample size. So that's what we have here. So the probability that a person selected is neither a woman nor science major. So it be only men who are non-science major. That would be 110 over 400. That's why if we can cancel, we break the smallest fraction. Are we okay?
Yes, sir.
Good. Thank you. Then we'll look with these examples, we'll continue to look at some axioms of probability. Let X be a sample space or a finite sample space, and A be an event in the sample space. So A is just a subset of what? Your sample space. And S is just a collection of all possible outcomes, where A is just a set of some of the outcomes of the experiment. Then, in the axiomatic definition, the probability P of an event A is a real number assigned to the number of events in that event, the number of outcomes in that event, which satisfy the axioms that we are coming to do. Axiom 1. The probability of any event should be between 0 and 1. When this, it can be 0 or it can be 1, or it can be between 0 and 1. So the probability is a number between 0 and 1. So we can have 0, we can also have 1. When the probability is 0, it means what? The event is what? A null set or an impossible event. When your event doesn't contain any value, it's an empty set, then we have the probability to be 0. When your event is equal to your sample space, then you have your probability of the event to be equal to 1. So that is what the axiom 2 is telling us. The probability of our sample space is 1, and the probability of a null set or even or an empty set is equal to 0. Axiom 3 is saying that if A and B are mutually exclusive events, means that A and B doesn't have any element in common. When they are intersection, is an empty set or a null set. A union B will be equal to the probability of A plus the probability of B, which means that the union of the event will only give you their individual between 0 and 1. So it can be 0 or 1. So it's 1. The probability of a null set is 0. The sample space just if you have to divide 400 by 400, 50,000 by 1,000, you will get 1. If your sample space is 100 and your total sample 100, if you divide 100 by 100, it will give you also 1. That is why we get that. Then if the samples is not finite, then
probability.
okay. So I'm saying that assuming your A1, A2, A3, A4 are events which are mutually exclusive. If we say mutually exclusive, it means that when I take any two of the event, their intersection will give us an empty set. Is that okay? As we can see here, the intersection of A1, AI, and BJ is what? Come again? Yes.
Hello, sir. So please, does that mean that let's say the values that will be in the set A and set B, they will be different?
They'll be different, right? That's what we mean. Yes.
Okay.
If there are A, B, C in what? In A, B will not contain any of the elements in A.
All right, sir. Thank you.
Okay. So we say that they are mutually exclusive. Their intersection is an empty set. So if that is how the events are, then the probability of their union will simply be equals to the sum of their individual events. So that is what we have here. Probability of A2, probability of A3. And when we add all of them, that becomes the probability of A union B union A1 union A2 union A3 union A up to infinite. So we take an example. This means, for instance, A1, A2, A3 are events that cannot occur simultaneously, meaning they are mutually exclusive. Then the probability that one among them will occur is the sum of their probabilities. For example, the probability of either a 2 or a 6 in a row of a dial is what? 1/6 plus 1/6, that's 2/6. So the event that a 2 will occur or a 6 will occur will just be their individual probabilities. We add them together, and that will give and 2/6 1/3. Meaning that event A and event B, event A that's 2, event B that's mutually exclusive. Okay, we also look at some elementary probabilities. Probability 1. Probability of A complement of event A complement is equal to 1 minus the probability of event A. We know event. When we consider the entire sample space and we choose event A, any element which is in A, which is what in the universal set but cannot be found in A, is the complement of A. So the probability of A complement is the same as 1 minus probability of A. We call this as a complement property. That property 1. So this means that if the occurrence of an event A is P of A, then the probability of non-occurrence of the event A, that's the complement of A, is probability of not A occurring, because 1 minus the probability of A. It means that the complement of A plus the probability of A should give you 1. So for instance, if the probability of obtaining a 6 in the rule, the probability of not obtaining a 6 is just 1 minus the probability of obtaining a 6, which is 5/6. Property 2 says that the probability of a null set, that's an empty set, is equal to 0. That the probability of a null or empty set or an impossible event is 0. Now, property 3 is saying that the probability of a union, which we call addition rule, of event A and B, event A union B, equals probability of A plus probability of B minus probability of A intersection B. In these two events, A and B, A is elements A and B have something in common. What they have in common is the A intersection B. So if A and B are not mutually exclusive, then the probability of A union B will simply be equals probability of A plus probability of B minus probability of A intersection B. The final one says yes.
Yeah, please, the probability 3. Can you do some quick because the A intersection is going to be A times B.
No, it will not. We have not reached there. We can multiply A times B. Let's look at the two-set problem.
Okay.
I'll be able to write now. Okay. I hope you can see my screen.
Yes, sir.
Yes, I can.
Assume this. Oh. Okay. This shaded portion includes and the probability of B.
Sir, please, someone is making noise at the background.
Benedicta, please, you are disturbing us, please.
Please, Benedict, can you mute your mic, please? So I'm saying that this is a two-set problem. We have A intersection B, which is shaded here. B is considering all of this area. Is that okay? Which has counted the intersection once. And if I find it also counted the whole of it, which has counted this intersection twice. So it's telling that has counted this area here twice. For you to get the probability of A union B, when you have two sets, you find A union B. The ones that occurred twice will only count it once. Is that okay? So your addition rule is saying that we should take away one of it because we have counted this shaded portion twice. We have to take it away. So we have this rectangle which has this set A and B. So let's say A contains 20, B has 30. So here is 5, here will be 15, and here will be what? 25. So B only is 25, and A only is 15, and 5 will be what? B that's in what? A. If the total is what? 15 plus that is what? 45. So your universal set equals 45. Then your probability of what? A will be equals to 25 over 45. And your probability of B will be equals to what? 30 over 45. When you add these two, it will be greater than 1. Is that okay? So we need to subtract the probability of what? A intersection B. That is 5 from it. That will end up getting the probability of A union B. So that is what we mean by the probability. Property 3. Is that okay now?
Yes, sir. Thank you so much.
That's what we refer to that. So that gives us an example of if A and B are what we're talking about. Nothing common. When they are not mutually exclusive, your are not mutually because there is intersection. The intersection is not there, so they are not mutually exclusive. So this is mutual, and this they are what? They are not mutually exclusive because they have something in common. So if they are like this, then we can say the probability of A union B is defined as probability of A plus probability of B because their intersection is 0. But if they are not mutually exclusive, then you need to go minus the probability of the intersection. We will look at it in our later if A and B are independent. It's then that we will multiply probability of A times probability of B. But if they are not independent, we cannot multiply that. So the same way, if you have 3 events, A, B, and C, and they are intersected, then we can have probability of A union B union C as probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of A intersection C minus probability of A B intersection C, then plus probability of A intersection B intersection C. The reason being that if I have this 3 sets, if I find probability of A, I'll get the whole of this. So I've counted this once, I've counted this one, and I've counted this place also. When I consider this, I've counted this one, I've counted this one, I've counted this one. So this one becomes 2, this becomes 2, this is 1. Are we okay? When I consider the last one, this becomes 2, this becomes 2, and this becomes 3. So you have counted the 3 sets 3 times. Year 2, year 2, year 2. So if we subtract this, you subtract this, you subtract this, you have taken away the 3 sets. So what it means that we need to add it together. That's why we have plus probability of A intersection B intersection C. Any question? Okay. Let me explain these work examples, then we can end for the day. Suppose event A, B, and C have probability P of A 1 over 2, P of B 1 over 3, and P of C 1 over 4. Furthermore, assume that A intersection C is empty, a null set. B intersection C is a null set. And probability of A intersection B is 1 over 6. So if I draw my 3 sets, I have this is your A, I have B, then I have C here. So this is A, this is B, and this is C. They have been told that B intersection C is a null set, so they don't have anything in common. A intersection C is also a null, they don't have, we will have intersection B as 1 over 6. So this is how your event will look like. We have to find the probability that A intersection B complement. A intersection B complement. A intersection B complement. A intersection B complement. But the first one, A intersection B all complement. B is the A intersection B complement. C is A union B all complement. D is A intersection A complement intersection B complement. Then E, A union B union C. So that's the solution here. First, A intersection B all complement is the same as probability of 1 minus what? B intersection what? A. The complement property that we learn. So that will be what? 1 minus 1 over 6. So that will be 5 over 6. Your B complement is what? This section, this section, this section, and all of this. That will be B complement. So we only subtract this from the total. That will give us what? 1 minus 1 over 6. When we use the relation A equals to A intersection B complement union A intersection B complement, this will give us what? A. So with that, the probability of A would now be probability of A intersection B complement union probability of A union A intersection B. So when we separate them, since they are independent, since they are mutually exclusive, then we can have probability of A intersection B complement plus probability of A intersection B. However, we know probability of A intersection B, we know probability of A. So all that we left with, we don't know probability of A intersection B complement. So we have 1 over 2, and then we make that a subject. Probability of A intersection B complement, and we'll get what? Half minus 1 over 6. That gives us what? 1 over 3 as the probability of A intersection B complement. Then finally, probability of A union B complement, the same as 1 minus probability of what? A union B. And probability of A union B, that is what we have here. Probability of A plus probability of B minus probability of what? A intersection B, which you have plus 1 over 3 minus 1 over 6. And that is giving us 1 over 3. Finally, probability of A complement intersection B complement is the same as probability of A union B all complement, that to be equals to 1 over 3. Using De Morgan's law, which we learned in maths. Then he is saying that it follows that A union B intersection C is also an empty set. So probability of A union C is 2 over 3. Probability of C is 1 over 4. Then this of a probability will be given as this, which is a probability of A union B plus probability of C. That's 2 over 3 plus 1 over 4. That is what? 11 over 12 as your probability. So, any question? Okay. So I want this to end here so that we'll continue learning next week. But I'll be sharing this slide with you, with your class rep, so that you can have a look at it. When you have any question, we talk about it over next week. Yes, Victoria, you have a question. Your hand is up. Kindly go ahead.
Hello, sir. Please, what's the actual difference between a sample point and an event? Because they all deal with one possible outcome.
They are different. A sample point is any outcome, any single outcome of an experiment. Whilst an event can be one outcome, can be two, or even can be an outset. So an event is a set containing what? One or more events or one or more outcomes. While a sample point is just one outcome of an experiment.
Okay, thank you.
Is that understood?
Yes, please. Sir, please, and then again, can we please get the recording of this section?
I will try my best and find out where it's being saved so that I'll send it to you.
Okay.
It's being recorded anyway, so I'll let you know.
Okay.
The chat.
Come again.